Hello everyone and welcome to the Game Engine programming series where we write a game engine from scratch. Now that we are able to render objects, we are a few steps away from making the scenes in our game look more realistic. We need lighting, shadows, textures and post-processing effects in order to get the renderer to a point that it can be used for gaming. Today we start with lighting the scene, and the first step in doing this is the ability to add different kinds of lights to our scene. So in this video we are going to write the code that handles the light data. Like in the real world, we can't see anything if there is no light in the visible spectrum to illuminate the environment. In computer graphics, we can approximate lighting with various models. In rasterizing renderers, it's computationally expensive to account for the light that has been scattered around the environment before reaching a surface. Although newer ray tracing hardware can do this type of lighting to some extent, for rasterizing pipelines, we can approximate the average color and intensity of the environment using an ambient light. As you can see, ambient light doesn't depend on viewing angle and the orientation of surfaces in the scene. Therefore, everything is affected equally, making all objects appear flat. So ambient lights only have color and intensity. Position and direction don't make sense because the light is coming from everywhere and from all directions. In general, at most one ambient light is enough for most purposes. Therefore, we don't explicitly implement them in the lighting system, but they can be passed as part of a global constant buffer to the shaders if we need this type of lighting. When the light source is very far away, the rays that originate from that source will seem parallel when arriving at the scene. Because all rays are parallel, it doesn't matter where objects are with respect to the light. Each object will be equally lit, just as was the case with ambient lights. However, they are only lit on the side facing the light source. Directional lights can have different intensities and colors. Examples of directional lights are the sun and the moon. We can have emissive objects within the environment, like lamps and spotlights. Local light sources that emit in all directions can be approximated using a point light. A point light doesn't have a size, but can have a position, intensity, and color. We can fine-tune this model by defining how fast the light loses intensity as objects get farther away from it. This is called attenuation or fall-off. We can also define a range beyond which the light doesn't affect any objects. This is important for optimizing rendering, where we don't want to calculate lighting for pixels that are not affected by a certain light. If a light source doesn't emit in all directions, we can often approximate it using a spotlight. Spotlights have the same properties as point lights, however, they also have a direction. We can define the cone of the spotlight using an angle with respect to the light axis. We can use another angle to define how quickly the light falls off outside the cone. These are the light types that we are going to support in Primal Engine. However, there exist more realistic lighting models that we'll be likely to implement in the future. These are area lights, which are lights that, as the name suggests, have an area from which they emit light. This is closer to how light sources are in the real world and therefore look more realistic. Today we will start with directional lights as they are the simplest to implement. Since directional lights don't have positions, they can't be excluded from the scene in any meaningful way. That's why we call them non-callable lights. All light types that have a position and an effective range can be called from regions where they have no effect, which we'll be implementing when we do light culling for the forward plus lighting. Before we start though, I'd like to explain how lights are grouped together. Imagine a building with 2 rooms, and each room has a number of lights that illuminate each space. Obviously, it would be a waste of computation to do lighting for the room that's not visible to the player. So we can either disable those lights or add them just before the player enters the room. And then we disable or remove the lights in the room that the player left. Although that works, it's quite inconvenient to keep track of which lights belong to which room and when and how to turn them on and off. This is further complicated if you would have more rooms. Instead of doing this, we can group the lights in sets, which we can switch between depending on where the player is. If we allow only one light set to be used at any time, then switching lights is simply a matter of setting a set as active when the player enters the room, and all other lights will automatically turn off. The API for lighting is similar to the camera in that lights are represented by this class that is used to tap into the internal light data. So we can just copy and paste our camera class and rename it. As I explained earlier, we have different types of lights, which we can put in this enumeration. Of course, light class has rather different properties, so we get rid of all these member functions. However, we keep the type and entity ID accessors because those apply to lights as well. As for the camera, we also have a dedicated ID type for our lights. In addition, we have a key that indicates to which light set each light belongs. This is a 64-bit integer that may have any value. All lights with the same key will be added to the same collection of lights. I also add an extra function to get this key. In this episode, we are going to add support for directional lights only. So the only properties that we are interested in for rendering are whether or not the light is enabled, the light's intensity, and its color. I'm going to define data structures that can hold data that's specific to each type of light. For now, directional lights don't have any properties that are different from other types of light, so the struct is empty. Although we are not going to work on point and spotlights yet, I'll just add them here to show how they are going to be used. So for point lights, the only properties that don't apply to all light types are the attenuation and range. I'll explain these properties more in detail when we implement these lights. In short, attenuation describes how the light falls off as a function of distance, and range is the maximum distance that the light can reach and affect other objects. For spotlight, we also have attenuation and range, and in addition, we have the cone angles for umbra and penumbra. Umbra defines the volume that is fully lit, and penumbra is the fall-off from the area that is fully in lights and the area that's fully outside of the spotlight's cone. Now we can create light init info that can be used for creating lights. All lights have a light set key and the entity ID of the associated game entity. We also need to include the light type. Other properties that apply to all light types are the intensity, color, and if the light is enabled or not. Finally, we add a union that contains specific data for each light type. Next, we need to expand the render interface for lights. For this, we can again copy the code that we have for camera, except now we have an extra parameter for light set keys. Now we need to define the parameter types for setParameter and getParameter functions. This has again the same structure as for the camera. For now, the only parameters are for the directional lights. We'll add extra parameters when we implement other light types. In the high-level renderer, we add two more functions for creating and removing lights. We are going to implement these here in the CPP file. Like most other functions here, they just call the function pointers from the renderer interface. Now we can implement the member functions from the light class. In each of these, we call a setter or a getter function with the corresponding parameter enumeration to set or get the data. For the getters, we create a local variable to which the data is written and we return it. I see I forgot to add a return type for these functions, so let me correct that. And we can continue with the remaining functions. Also, don't forget to set the correct parameter enumeration, otherwise it won't work. It would be nice to have a way of checking if we are using the right parameter enumeration at compile time, but I can't really think of any way to do that, so feel free to suggest your ideas. Now that we got the high-level API, we are ready to implement the low-level functions, which is the code that actually does the work and handles the data. For this, I'll add a new header file, which I call the 3d12light.h. While Visual Studio is testing my patience again, I'll try and add the low-level function declarations here. Where we set the render interface function pointers for the D3D12 renderer, we can assign these functions for creating and removing lights, and getting and setting light parameters. Now we can go ahead and implement these in the CPP file for the 3D12 lights. I'll leave these empty for now, because we need to define what a light set is at a low level and how the data are represented for lights within each light set. Normally, we would define a structure that holds all data for each light. However, because we want to send part of the light data to the GPU, I'd like to separate the part that we send to the GPU from the part that we need for bookkeeping. This is what I call the light owner, which has an entity ID and an index to an array that contains the rest of light data. We need an index because in case of point lights and spotlights, we want to pack the GPU data in a tight array, and therefore the index of light data within each array isn't necessarily the same as the ID of our light owner. The light owner also has the light type and a boolean for is enabled. We can define the light set class next. We can have multiple light sets which we can access in an unordered map using a 64-bit integer key. In light set class, we need a function that will add lights to the light set. For now, we only want to implement directional lights, which are non-callable. Later, we'll handle callable lights. Before we can add lights, we need some containers that will hold the data. The light owners will be put in a free list. In the same way that light owners point to their GPU data using a data index, we need to have a way for the data to point back to their owners. So we need an array of light IDs which contains the index to each owner. Now we need to define the part of light data that is sent to the GPU. This is a structure that is shared between C++ code and HLSL code, so we are going to put it in common types. In addition to direction, we need an intensity and color to define a directional light. We also make sure that the structure is padded to a size that is a multiple of 16 bytes, which is important for reading the data as a structured array in the shader. Going back to the lightset class, we need an array that contains GPU light data for each light. In case of directional lights, we are not going to put effort in making sure that the arrays are tightly packed. This is because the number of directional lights in general is and should be low. In real life, the only light sources that can be considered as directional lights are the sun and the moon. Sometimes we can use directional lights for really bright spotlights that are far away, such as those in large stadiums, but in general most lights can and should be approximated by some type of light with limited range. Since directional lights aren't tightly packed, we can search for an available slot in light data array. If a slot exists because of a removed light, for example, we can put the new light in there. Otherwise, we'll append it to the end of the array. So we get the index to an available slot or the new one that we appended, and then write our data to that index. Finally, we create a light owner for our data and set the indices in both the light owner as well as the light data and return the light. I'm sorry, but I really have to restart Visual Studio because it's exceptionally uncooperative today. I'll also delete the .vs folder to get rid of the garbage it accumulates over time. Well done, Visual Studio dev team. Well done. Let me reopen the files where we worked in. The next function that we need to write is one that removes lights from the light set. Before removing any light, we are going to disable it. This has some packing benefits for callable lights that we are going to implement later on. In case of directional lights, we set the owner's ID to invalid. This is how we mark the available slots for removed lights. At the end, we simply remove the light owner from the free list. The enable function sets the isEnabled field in light owner and does nothing else if the light is directional. For other types of light, this function is going to move the data around such that we always end up with a tightly packed array. This is where I'd like to stop for today. In the next video, we are going to write the rest of LightSet class, as well as implement the low-level API functions that create and remove lights, and set our getLight properties. As always, thank you for joining me, and I hope to see you next time. Thanks for watching. If you like this video, please feel free to like and subscribe. If you join me on Patreon, you'll get access to the code on GitHub, so you don't have to type everything over from the video. Plus, there are also other nice goodies and rewards exclusive to my Patreon supporters. Please use the link in the video description to check them out. I hope to see you next time. Until then, take care and happy game engineering!